Okay, before I do the promised application involving logarithmic equations, I want to just try a couple more just because I know these are very challenging. Let's take a look at a couple more equations just sort of as bonus here. Again, here's a logarithmic equation, log base 2 of x plus 2 minus log base 2 of x minus 5 equals 3. Remember, the idea is to combine as one logarithm. How do I do this? The log base 2 of something minus log base 2 of something, I can combine those as one logarithm, right? By the property that says what? Log base 2 of what? X plus 2 divided by x minus 5. So the difference of logs becomes the log of a quotient, right? Remember, it's log base 2 of x plus 2 divided by x minus 5. And the reason I can do this, remember, logarithms are exponents, and when I'm dividing like bases to different powers, what do I do with the logarithms? What do I do with the exponents? I subtract them. Okay. And this is still 3. So now I've got a single logarithmic, right, expression equal to 3. Log base 2 of something is 3. So what is this exponential form of this logarithmic equation? The base is 2. The exponent on the base is 3. So 2 cubed is x plus 2 divided by x minus 5. And what is 2 cubed? 2 cubed is 8. So if I multiply both sides by x minus 5, I get this simple linear equation, right? I can distribute the 8 and subtract x from 8x gives me 7x. Add 40 to both sides, I get 42. And dividing by 7, I get 6. Okay. So, do I just go on and say x equals 6 is my answer, I'm done, end of story? No, we need to make sure we check. Remember, we saw an example in the last video where we had no solution, right? That may be possible. Notice here, this says that x minus 5 must be greater than 0, so x is greater than 5. This says that x plus 2 must be greater than 0, so x is greater than what? Subtract 2, negative 2. So we have to have something that's greater than negative 2, all right? In fact, we have to have something greater than 5. This is more restrictive, right? Because of this one here. So since x is to be greater than 5, well, we're 6, we're 7, right? And we can check still, right? If I go back and check, I can check by plugging in x equals 6. Log base 2 of what? 6 plus 4, 6 plus 2, 6 plus 4, 6 plus 2, minus log base 6, log base 2, I'm sorry, I'm just all kinds of messed up. X equals 6. Log base 2 of 6 minus 5, which is 1. Does that equal 3? Does that equal 3? So, of course, this is 8. What is log base 2 of 8? What is log base 2 of 8? What's the power of 2 needed to get 8? 3. Right? 2 cubed is 8. Minus what? What's log base 2 of 1? 0. Power of 2 needed to get 1 is 0. Is 3 minus 0 equal to 3? Yes. Okay. So it checks. So I have the correct solution. X is equal to 6. Okay. Let's try one more. Another one, notice on this side we have logarithm, and on this side we have logarithms. We have 2 logarithms. These can be combined as a single logarithm by the property of logarithms. When I add logarithms, what is that? That's the log of a product, x times 4, or 4x. Right? So the log of a product is the sum of the logs, because when I'm multiplying like bases to different powers, I add the powers. Okay? So I have log of x plus 4 equals log of 4x. That's kind of interesting. Remember what we said, though, if log of A equals log of B, then A must equal B. Another way of thinking about it is I can exponentiate both sides of this. In other words, I can write this as 10 to this power, 10 to this power, And 10 log of x plus 4 is just x plus 4 because that's the inverse operation for the log base 10 function. 10 to the x, the exponential function base 10. Same thing here. And so there we go. X plus 4 is equal to 4x. Can you solve that equation? Yeah. Subtract x from both sides. I get 4 is equal to 4x minus x is 3x. And then divide by 3. X is equal to 4/3. This one I can actually check because I have a log button in my calculator. So if I do this log of x, and what is 4/3? It's about 1.3. Don't approximate it though. Just write it as 4/3. 4 divided by 3, right? Plus 4, right? And that's supposed to be equal to this stuff. Let's see. Let's just see what I get here. I get that number, which is about, right, which is that side. So is this side the same thing? I've got log of x, which is 4/3, plus log of 4. Is this also, yeah, look, again, it's approximation, but we can see we feel pretty good that both sides are equal in this case. Okay, so it checks. Okay, let's look at a final example, which is an application. So students in a psychology class took a final exam. As part of an experiment to see how much course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. Boy, can you imagine just taking every month the same final exam over and over again? They must have paid these students something, right? At any rate, the average score for the group, which is the function f of t, where t is the months since the first exam was taken, is this models the average score for the group, where t is the number of months after the initial final exam was taken. So how long will it take the average score to be 50? So notice as t increases, the natural log of t plus 1 gets bigger and bigger, and we're subtracting from 88. So notice that t equals 0. Notice that f of 0 is 88 and minus 15 log of what? 0 plus 1 is 1, but the natural log of 1 is 0, so it's just 88. So in other words, the original average was 88. The average score was 88 when they first took it. But as time progresses, we're taking away from that 88. It goes down. So the question is how long until it's 50? So how long will it take the average score to be 50? We want to find the value of t such that f of t is 50. So I want to solve the following equation. F of t, which is what? 88 minus 15 natural log of t plus 1 is what? 50. So I want to solve this equation. How do I solve this equation? It's a logarithmic equation. Here's the logarithmic expression. Right? This is ln, by the way, log base e. I want to get that by itself. So what do I need to do? I need to first of all subtract 88 from both sides. 88 minus 88 is 0. I get negative 15 natural log of t plus 1. 50 minus 88 is negative 38. And then what? I want to get the coefficient in front of the natural log to be 1, so what do I need to do? Divide both sides by negative 15. And I get the natural log of t plus 1. Negative divided by negative is just positive. 38 divided by 15. Now there's no common factor between 38 and 15, so I'm going to leave that you can't simplify it anymore. But now what? I've got the natural log of something is 38/15. Well, what is this in exponential form? The base is e, the logarithm is 38/15. So e to the 38/15 power is t plus 1. Or, solving for t, it's e to the 38/15 minus 1. There's your answer. But you're not going to tell someone, yeah, it will take how many months? E to the 38/15 minus 1 months. No, this is exact, yeah. Well, now we really want to know what this is, and so we want to come in and, of course, approximate this, which is fairly easy to do. E raised to what power? 38 divided by 15, and then minus 1, right, gives me that. And I'll just say, I'm just going to go to 1 decimal place, right? I mean, no sense in being real accurate about it in terms of this, because this is month. So how long will it take? So go back to the question, how long will it take the average score to be 50? And so the answer is about 11.6 months. Right? So if they're taking it monthly, you know, the 11th month, the score should be, the average should be slightly more than 50. By the 12th month, it should be a little bit less than 50 is what we're saying. You know, this model is approximately just shy of 12 months. But somewhere in there, right around 11 or 12 months, the average score would be 50. So, you know, what this is saying is, you know, as time progresses, you lose understanding, you lose things, you forget things. Like mathematics, if it's been a while since you did factoring or solving equations, you know, you need to refresh yourself about these things. It is very important that you see this, that as we go through this, that the skills that we're learning, they build upon themselves, right? And this is no doubt an example of that in this section on exponential and logarithmic functions and now equations. We're using all the things we've learned. It's a cumulative effect. Okay, so there's a good smattering of exponential logarithmic equations. It's now your turn to spend some time on solving log equations.